This is LeetCode 1971, find if path exists in graph. So in this question, we're given a bidirectional graph with n vertices. So the vertices are basically each node here, 0, 1, 2, each one of these a vertex. So that's each node. And within here, we're given a 2D array of the edges, and each edge is essentially the path from like 0 to 1, that would be one edge, and from 0 to 2, that would be one edge. So each one of these lines is the edge. Additionally, in this question, it specifies that each node is not connected to itself, and there's only one edge to each node. So in this question, we're told to determine if there's a path from one source to the destination. So that's from node to node. So in this example, we're checking for if there's a path from 0 to 2. So in here, if we start at 0, is there a path of edges that goes to 2? And there is, because it's all connected. In this question, though, is there a source from 0 to 5? There's not a source, because if you go from edge to edge, you come to a dead end for each one of these. So the strategy to solve this is either a breadth-first search algorithm or depth-first search algorithm. I saw a lot of solutions creating their own graph, but I found there was a much easier way to do all this stuff. So instead of using a graph and doing the depth-first search, you could just simply do it without a graph using a stack. So I chose a depth-first search because I felt like it would probably be the most efficient for this question. Depth-first search and breadth-first search are basically the same. Time complexity, it just depends on the type of graph you have. So let's use this as an example for depth-first search. So let's say we have these nodes, and we start at 0, and we want to get to 4. So 0, there's a 4 here, 1, 2, 3. If we were doing depth-first search, if we start at 0, from here, we'd directly go to 1, and we'd add the 0 to the stack, and then we'd add the 1 to the stack. And then from there, since it's depth-first search, we just continue that direction. So depth-first search, you just go all the way in one direction as you can. Then from there, you basically retrace back. Go all the way you can in that direction, all the way you can in that direction. So depth-first search would solve this specific tree going 0 to 1. And then from 1, it'll see how far it can go right. It'll go to 2. So you'd add the 1, then you'd add the 2. And from 2, you'd go all the way right as you can, so you get to 3. However, once you're at 3, it's a dead end. So from there, you get rid of 3, get rid of 2, get rid of 1. Now you're back at 0. And now you continue checking all the adjacent nodes to 0, and it would lead you to 4. So once you get to 4, you notice, oh, that equals the destination. And from there, you have the answer. Now, breadth-first search, on the other hand, would solve this question a lot differently. And for this tree, it would be faster. So breadth-first search it would also use a queue. It would go, you'd start at 0, and then you just check all the adjacent nodes. Then from there, you check each one of their adjacent nodes. So almost like a wave pattern, whereas depth-first search is just all the way one way, then all the way one way, all the way one way. So depth-first search here would start at 0, so you add 0 to the queue, then it would go to 1. Now, since it's depth-first search, it won't keep going down that way to 1. It'll check the rest of the adjacent nodes of 0, which would then be 4. And it would get the destination a lot quicker. Now, if for this question you wanted to get to 3 using breadth-first search, you'd go 0, 1, 4. And then from there, you check all the adjacent nodes of 1, and then all the adjacent nodes of 4, which 1 has 2, so you add 2. 4 has nothing, so you just continue. Now the next one is 2, check 3, and then you have the answer. So understanding that, to solve this question, we're going to want to, I'm going to be using depth first search. However, with depth first search, we're also going to want to keep track of each node that we visited to prevent duplicates. So like in this one, 0, 1, 2, let's say the destination was 5 and 5 isn't in here. You basically check 0 to 1, 1 to 2, 2 to 0, then yada yada, you're just in an infinite loop. And that would be the same for this as well. You'd just be in a loop, not realizing that, because it's also bidirectional. You wouldn't realize that, oh, you've already visited it. So bidirectional means that in this specific question, you could go 0 to 1, and then from 1, you go back to 0, and back and forth, which means you need to keep track of each node you visited. To code this problem, I'm going to use depth first search, and the strategy is basically we're going to add every node to the set, and from there, that's how we check if the node we're going to next is unique. And to do so, we're going to add a set integers. We're going to also want a stack integers. So we're basically going to loop through all the values in the stack, and every value in the stack is a vertice or vertex, and every vertex is a node pretty much. So our stack is going to be filled with unique nodes that we haven't visited yet. And from there, we're going to check the adjacent edges that that specific node can go to. So to start, we're going to want to have a while loop checking if the stack is empty. Now, I added this, let's do that. I added this test, basically making sure that it just helps go through the first initial run through of this while loop correctly. And basically from here, each while loop, we're going to want to check what the current node is that we're at. And to do so, I'm going to instantiate a current source. I'm just going to set it equal to 0. I'm not actually going to use this value, but from here, we're going to check if we're on the first run through. And if we're on the first run through, we're going to say the current source is equal to source, which is the initial value that we're given. Otherwise, we're going to want to say the current source is equal to the unique node that we're currently at that from the stack. To do so, we're going to do stack to pop. Once we're at this point, we have the correct source node, and we're just checking if this source node has unique edges. And to do so, we're just going to do a for loop. And from here, we're going to check if edges I0 equals the source. So if we were looking for 1, hypothetically, we're going to check if here, we're going to basically check all of the first or the 0 index values if any of them equal 0. And if they equal 0, that means there's a path from 0 to somewhere. Now you could do the same thing for this one. However, we'd have to check I1 to find this value right here. So we're going to do this for loop once, and then we're going to check the left and the right index values. And it doesn't really matter because these are bidirectional. So if it goes from 0 to 1, that's the same as going from 1 to 0. So now we're at a good spot to check if this value that we're at, which means that we're at basically an adjacent edge to the current source, we're going to see if this path is the destination. So we're going to see if edges 0, 1, which would be the opposite index, because each of these have either index 0 or index 1. Each of them have 2 indexes. We're always going to just check the opposite one. If the opposite index equals the destination, we're going to just return true, because that's the case we're looking for. Otherwise, we're going to want to add the node that we were just at, and now and then also we're going to want to check if this path is a unique path if we haven't visited this node. So in this scenario, you have the loop. We're just going to check if this is a loop or not, if this is a unique edge path. So if set does not contain, edges, the opposite edge, that means that we can add the opposite edge to the set and the stack. From here, we're in a good spot. However, our code currently is not checking all of the possible source areas. So we're checking if index 0 equals the source, and if it does, we add it. We also need to check if index 1 equals the source. The graph is bidirectional, which means that these values can flip-flop. So the way we have it so far, if we were to go through this list, we'd check here if the index 0 equals the source, which the source is also 0, that means that we'd add it. So right here, we'd catch this one, which is this line right up top, but we'd miss this one right here, which is the other adjacent edge case. All we have to do to solve this is the exact same thing, but just flip-flop the numbers. And that'll solve for all of the values, and we don't have to worry about these duplicating, because whenever we add to the stack, we check if it's a unique value because we use a set. So all we have to do from here is return false, basically when this while loop never detects the destination. And we also need to make sure here, I forgot to add this, that we make test equal false, because this should only go through once for the initial run through. And also we need a base case if the source equals destination, we need to return true, which is just one of the cases they give. And this should give us a really quick, efficient time complexity, efficient memory, everything in, I'd say, the easiest way to solve this question. I used a depth first search with a stack, set